let's take this one. Okay, now one more very generalized thing once again. In the Gaussian surface, so what is this green color? It's a Gaussian surface. Only what happened, a point charge can be there, that at center, or point charge can be anywhere. No, point charge can be anywhere. Then next, a charged body. This is some body. This we know, solid charged hemisphere. So inside the Gaussian surface, only point charge that way at center, need not anywhere point charge can be. Next, can I bring a body like a laminar body, like a disk or a sheet? Yes, you can bring. Can I bring some 3D object? Yes. Will it be? It should be at center. Nothing to do. It can be anywhere. In all the cases, what is the net flux? The net flux is given by the formula. So it doesn't matter. No, what is there? Like this one, how much of charge enclosed? That's all. Is it a point charge? Is it a laminar body? It's a three-dimensional body, irrespective of that one. I think this is what going to help us a lot next when we get into the determination of electric field. Okay, this one, any doubts, please do clarify. Sir, what is electric flux? Again and again, it will give us the better information of the lines of force. Am I right? The better information of lines of force is what provided by the electric flux. Than saying lines of force, no, I'll be more interested in expressing that lines of force in terms of electric flux here. Now, I have kept a Gauss law to determine the field due to a charged body. So first, let me start with a point charge. No, a point charge I kept. We know what is the electric field due to point charge. Am I right? We know what is the electric field due to a point charge. At a point P, what is the electric field strength? How much it should be equal to KQ by R square. So then why you're asking? Let's use this. Let's start with the simple with the point charge. First, we'll find out electric field due to point charge using Gauss law. Then we'll extend for different bodies. Then we'll see what conditions will come. How far this Gauss law is going to help us a lot. What I do is like, there's a Gaussian spherical surface. I'll assume a elemental surface. So what is the surface ds? Now flux linking that d phi is equal to integral of E bar dot ds. I'm not bothered flux. Let me write, no problem. So E bar dot ds. What is the net flux linking the total Gaussian surface? That should be equal to charge enclosed by epsilon naught. Then I am going to pick up a surface. That one. You take any point on the surface, will be at a distance r, and everywhere E bar will be parallel to n cap. So therefore, so what will happen to this? This will become E ds cos 0 degrees, because every point, it's like a, take a point charge or take some LED glowing bulb, keep it at center of the glass shell. Then the light, what will happen to the light? Light will come radially outward. So everywhere, the direction of propagation of light will be perpendicular to the surface. And what is n cap? It's a unit vector normal to the surface. So you look at that one, at every point on a surface, E bar will be parallel to n cap. The ds is like a patch, one football patch is what I assumed here. So now at every point, we know at a distance r, what is the electric field strength? Should be constant. And angle between them is 0 degrees. So this will become integral of E ds. When I add up all such elements, all such elemental patches, what do I get? I'll get the surface area of this particular sphere or a shell. So how much it should be equal to Q by epsilon naught E into 4 pi r square. So what is the electric field now? Q by 4 pi epsilon naught r square. So I got expression for electric field due to point charge. Fine. So there's the expression for electric field due to point charge. Okay, now you can ask questions. Why you assume spherical Gaussian surface? Why not any other surface? There's a primary question. Okay, let's try. Let me assume some box. Gaussian surface is a box. What is the problem? Yes, there'll be lines of force. Then I assumed like a several elemental surfaces here. You can see this. At all points on the surface, what is E bar? E bar is different at different points. And or look at the angle also, here 0. What about here? Here some angle. Here how the n cap will be? N cap vector like this. What about n cap here? What about n cap here? So look at also the angle. Here the angle between E bar and n cap 0. Here angle between them is some increasing. Then again it becomes certain angle. Again it varies. So what is the problem here on this Gaussian surface? It's like a box. Huh? I'm asking you like a cubical box. It is kept at center. At different points on the Gaussian surface, the value of E bar is different and also angle between different. Then how the formula? The formula will end up like this. Flux is equal to integral of E1 bar dot ds1 bar plus E2 bar ds2 bar, E3 bar and so on. And what is the net charge enclosed by it? Q by epsilon naught. So what is the problem? The RHS we cannot solve. So, but what is our question? I wanted expression, no? Like, tell me like why I ended up here with answer? Why am RHS I'm unable to simplify. What is this one? ds1. Further, if you simplify this will be E ds1 cos theta 1. E2 ds2 cos theta 2. E3 ds3 cos theta 3 and so on. RHS, I think nobody can simplify this. So what went wrong? Gauss law wrong? No, the suitable Gaussian surface we could not assume. So therefore, whenever you are using Gauss law to find out to determine the electric field, what are the conditions you have to take care? You have to see that at all points on a Gaussian surface, the E bar should be parallel to n cap and E must be constant. Then if that is the case, if E is constant at all points, we know at additions are what is the electric field? E. Then everywhere E bar is parallel to n cap. Not only here, you can check here also. E bar will be parallel to n cap. Then angle between E bar ds at all points will be 0. Then the E will come outside integration. Then integral of ds, as we know, what is surface area of this Gaussian surface? 4 pi r square. I got the answer. So tell me like, what are the precautions I should take when I'm finding electric field due to Gaussian surface? Suitable Gaussian surface, we should assume. How to assume suitable Gaussian surface? As I'll follow the points. Points to be followed. Okay, I think I have brought here. Can we draw any desired Gaussian surface? The answer is no, no, no. Then what conditions are to be followed while drawing a Gaussian surface? These are very fundamental. Okay, the first thing, let me write it here. At all points on Gaussian surface, E must be constant. Not most, must. E must be constant. Second, at all points Gaussian surface, E bar must be parallel to n cap. Then this is the thing which you have to take care when you are assuming the Gaussian surface. If happens like this, then the equation will reduce to integral of EDS. I think then we can integrate, no? This will become E bar ds will become, now anybody can integrate this. Otherwise, what happened? E bar dot ds bar cannot be integrated, integrable. Then we'll not end up with the answer. So tell me now, what is the highest priority in using Gauss when it comes to Gauss law? Assuming suitable Gaussian surface. So a best example is like a point chart. Sir, I assumed here a what, like cubical box, Gaussian surface. Will not get answered, cannot be solved. Any doubt? Please do clarify it, because this will become very fundamental for you.